welcome to the course of Fundamentals of Micronanofabrication, and we'll be discussing the week 3 of this course. I am with BMRX for IIT Madras. So, with this course this week deals with the native fields, and the first problem here uh, is on ion implantation, and like we have to compare uh, which of the following would go with implantation and which would go with diffusion. So you guys can tell like so the first statement is provides like these are the five statements, and you have to tell like which one goes with which one, and at the end of the day you will have to say the should I can see the yeah, you can type now. I can see. Uh, Before I wasn't able to see. You all understood the question, yeah? So these are five statements, and you have to tell which one of them would go with the like would they go with iron implantation, or they will go with diffusion? That's the question. B. So they were saying B is okay. Let's see. No, that is what they say. Internet is a little bit issue. Anybody else has any answers? So okay, let's discuss. C. Okay. So anybody this first option, what do you think, sir? Regarding the first option? So B and C, the both you are saying it is implantation. So yeah, mostly it's implantation because we can grow arbitrary profiles with like with implantations at room temperature. We can control the energy of the like energy what controlling the energy, uh, accelerating like voltage, and we can get like a desired doping profile. So yeah, first one is implantation. So the second one is dopants are already activated by the end of this process. So both of you are saying B and C. So both of you are saying diffusion. So yeah, it's correct. Like yeah, in diffusion is done at a higher temperature, and they usually sit at the substitutional positions so that they can bond with the neighboring atoms. So uh, essentially, this is their diffusion because in implantation we need a annealing temperature for getting the dopants to activate it. And the third one is 100 to 300 nanometers silicon oxide can be used as a doping mask. So one of you says it's implantation, another one is says diffusion. It's for diffusion we can use silicon oxide as a mask because this thing the rate at which it diffuses in silicon oxide it is very slow, while in silicon it's like compared to silicon. But the same is not like implantation, we cannot say like that. So essentially, we use silicon oxide for as a doping mask for diffusion process. So it's diffusion. And the fourth was statement that low temperature soft mask works only the thickness of the mask matters. So this is more like it goes with low temperature soft mask. They are telling that in what do we say in this implantation process we use photoresist as a mask. So like we can tune the thickness, and there we can get the desired. We can't use silicon oxide here. So here it's implantation. It's more relevant to implantation. And last one is many silicon lattice atoms are displaced from their lattice positions, and hence annealing is required. So annealing is only required in implantation. So implantation, implantation, implantation. So C is the correct. Yeah. I hope everybody understood the five statements. Any doubts? You can tell. Voice is not clear. Okay. So, now it's okay. Now it's better. Okay. Yeah, some net issues are there. Yes. Okay. Anyways, you can go. So that's all. So the second problem. So this is a numerical. So in ion implantation method for doping silicon, the implanted ions damage the silicon lattice, yeah, and we need to heal it through a annealing step. So uh, here we have to calculate the healing time. So if we have a thing called if one implant ion displaces 10,000 silicon atoms and the implant range is 50 nanometer, so we have to calculate the number of implant ions required to first question is to amorphize 1 centimeter cube of silicon, and the second is what is the dose to amorphize 50 nanometer of silicon layer. So the density of silicon atoms is given. You all can try. Uh, I I hope everyone got the question. Yeah. So it's essentially to tell what is the required time, required ions that we need to that is needed to amorphize 1 centimeter cube of silicon, and that the number of atoms one ion displaces is given, and yeah. Can try. I think you need a calculator maybe. So I hope you are trying. Yeah. So regarding the number of number of implant ions required to amorphize 1 centimeter cube of silicon. So anybody has any approach like how to go on with this? So in this we actually need two things. So we have to see that how many like we have to get the like native silicon atomic density. So we have that. So we need to say like see that how much of that like from that native like native density of 1 centimeter cube, how much is displaced. So we need to find that out. So first thing would be that. So uh, you all can try once. Okay. Uh, let's do the first part. Yeah. Is anybody doing it like so we can start otherwise? Is anybody trying it out? Then we can maybe wait 2 seconds. Okay, let's do it. So the given is we have 5 into 10 to the power 22 atoms per centimeter cube. In 1 cubic centimeter, we have 5 into 10 to the power 22 atoms of silicon. So to displace this amount of atoms, we need yeah, okay, we must done it. Cool. So to displace it, we would need how many that is we have to calculate the number of ions to displace the whole silicon, like uh, 1 cubic area, 1 cubic volume. So we will need 10,000. 10,000 is one displaced by one implanted ion. So with this we get is 5 into 10 to the power 22 minus 4 is 5 into 10 to the power 18. Yeah, ions is needed for displacing to basically amorphizing 1 centimeter cube of silicon. Yeah, that's the first part. Essentially, the first part I think tells the answer. But yeah, so the second part is what dose is needed to completely amorphize 50 nanometer silicon layer. So uh, anybody has an like anybody got the answer? This answer 2.5 into 10 to the power 12 per centimeter square. Okay. So we know that for amorphizing 1 centimeter cube of silicon, we need 5 into 10 to the power 18 ions. Like we have this area as constant, and we will just go as a vertical axis. So we will just go down. So this area we are considering it constant as this uh, like uh, like we can also like yeah, in one process we see that this amorphizing it can amorphize as a like in a parallel like in a constant fashion. So it can parallel uh, like if we have so full this is amorphous. Yeah. So we can see what is the range here. So we'll go just like this. So we know that 5 into 10 to the power 18 ions per centimeter cube is needed. Okay. Is needed to amorphize it. Okay. Uh, so uh, so we have to calculate how much is needed to go down to 50 nanometer. So 50 nanometer we can write as 50 into 10 to the power minus 7. Yeah, centimeter to nanometer. So with this we find that uh, it comes to 2.5 into 10 to the power 12 ions per centimeter square. We just go down the line. We are not considering the other, like only the volume that goes this channel down the sequence. So with that we get 2.5 into the power 12 ions into centimeter square. Okay, this is also numerical. So in this we go into this post implantation anneal that is necessary to repair the lattice damage. So basically after we do a iron implantation we go for this annealing step. And so in this step, this like the dopants, they can diffuse also because this is a high temperature step. And this activation energy of dopant diffusion is 3 to 4 electron volt, and while for lattice repair is 2.3 electron volt. So there is a like difference in the activation energy, and we use this window of temperature, like we use this window of energy such that we can do like we can perform our repair uh, such that there is no significant diffusion. So for so there is this recrystallization thickness dr which is given. So for time t, what is the thickness that it thickness that the silicon recrystallizes, that is given with this equation, and the diffusion length of boron. So how much length it how much it diffuses in the silicon is given by this equation. So the thickness of the recrystallization thickness is this one, and the diffusion length of boron is this one. So what you have to find is, first one is the time required to heal or recrystallize 100 nanometer of silicon at 900 degrees Celsius, and on the same temperature, we have to compare. We have to see that how much boron diffuses in silicon. So I will also calculate together. You all can try. So value of KT is given, so directly you can tell. So this 100 nanometer is for the first thing is the DR here, the, the thickness that we need to. Yeah. D. Okay. Anybody else? So you calculated both the things or only the first thing that has given the answer? Okay, anyways, the answer is getting answer in MCQ is the main thing. But yeah, we will see how to get both the things. Anybody else got any other answers? anyways, we will proceed to the answer. So here, as I said, this recrystallization thickness is given. So that is the length we need to heal. So here that length is given 100 nanometer. So we will take 100 nanometer. Both, good, good. So 100 nanometer is equal to this 5.43 to 10 to the power 11 e 2.3. I think for for me it's coming around 69 point. What's this? 69.97. This value. 400. Yeah, and by dividing, you will get t is equal to 1.43 seconds. Yeah, this is the first part. So 1.43 seconds. The second is for the same time and temperature, how much does the boron diffuse in silicon? So in this, we have to put similarly, you have to put the values in the this formula LB equal to 7.6 into power 30. So we get so this you calculate, you will get this value of 0.3. So anybody has any doubts regarding this question? We'll move to the next one. So this is a theoretical question. So this is a question from the uh, oxidation of native films, formation of native films. So and it comes from the part of linear rate. So in initial minutes of oxidation, we know that the rate is linear with time, and this we can see that the rate coefficient of RNAs that we were like that they are represented with reveals that the energy barrier for oxidation of silicon is 2 electron volt for both oxygen and water vapor sources. So we have two methods of oxidation, the dry and the wet. So in both the things, the energy barrier is the same, 2 electron volt. And so you have to tell the reason for why the like which of these following statements tell that is the proper reason for the this phenomenon that the same energy barrier for oxygen and water vapor resources. So this is a multiple correct like possibility. So you can check all the statements and yeah. Anybody? Any guesses? Any of the statement you think is correct explanation for the B? C, D. Okay. And D as well. Okay. Anybody else has any guesses? Okay. So, okay, two of you told the things. So, okay, first, going with the first statement, the oxidation is limited by the rate at which silicon oxide interface oxidizes because the thickness of oxide is small in initial minutes of oxidation. So, yeah, understanding the first, we are here dealing with the initial minutes of oxidation. Okay. So in that initial oxidation minutes, we have to see that which one is the rate determining thing. So as the thickness is very low here, the 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 thing that is determining the thing is not the diffusion. Like diffusion is not a issue here. Diffusion is not a thing that is uh, limiting the process. So it's actually the interface of this silicon oxide where the oxygen has to diffuse, which happens relatively like faster now as the silicon oxide layer is very thin and but the main thing is it oxidizing the silicon here. So when it reaches this like here we can see this up diagram that when it reaches this silicon interface in the top right corner you can see, and when it reaches this position, now it has to oxidize this silicon. So uh, that is the rate determining step here. Uh, so here, this diffusion is not a issue. So the oxidation is limited to the rate at which silicon and silicon oxide interface oxidizes because this thickness is small, is initial minutes of oxidation is a correct option. Because here the interface needs to get oxidized and the diffusion happens relatively faster. So the B option is the oxidation is limited by the rate at which vapors diffuse through the oxide to the silicon oxide interface is not a correct option because diffusion happens uh, quite faster, quite rapidly. The rate determining step is this surface interface oxidation. And the C1 is the energy required to break silicon-silicon bonds is the barrier for both oxygen and water. So initially they need to form this silicon oxide. Okay. So there we need to break the silicon-silicon bond. Yeah. Otherwise this they can't interact with the oxygen. So that's why this 1.83 electron volt is similar to this the activation energy of this the both the oxidation process. Right? Like you can see this 2 and 2.05. It is uh, similar to the energy required to break the silicon silicon bond. So that's the reason. So yeah, this uh, uh, similarities due to this. And the diffusion barriers for H2 and O2 is this one respectively. But diffusion anyway is not a factor here. So that's that's uh, not correct in this situation. So in linear rate, it's the so all in all the linear rate the surface. reaction is a important factor, and the breaking of silicon-silicon bonds is one is another one. So that's why this energy there is a similarity in this similarity of SI bonds, energy of the silicon-silicon bonds to the activation energy of both the oxidation process. Plus for this different like facets of silicon, like 111 plane and 100 plane, it is like it is different. That's because surface reactivity, like what bonds they need to break and to get into this silicon oxide is different. So that's because this silicon. So that tells us that this interface is the major factor. Yeah, I think that explains it. So the second, the problem B, problem five is dealing with the parabolic ray. So it's the same question, but here we are understanding that we are to tell that what is the what's the reason for this parabolic like after some times when we get this parabolic rate after a few minutes of oxidation. So we see that this wet oxidation has a activation energy of 0.71, while this dry oxidation has 1.24 electron volt. So we have to tell this why the energy barriers are different in this region, and we have to tell the reasons too. You can see that the initial energy barrier was same, but now it's different. 0.71, and for dry it's for wet it's 0.71, and for um, dry is 1.24 electron volt. So yeah, it's a PNC. Okay. Others, please respond. You can also unmute and tell. You can type in the chat when it works. If you didn't understand the question, you can also ask. So anybody else? So with this question, we can see. Okay, so like as we discussed in the previous thing, so we got discussion of this. So the first statement is the oxidation is limited by the rate at which silicon oxide interface oxidize. So like we have to understand that after a few minutes of oxidation, the layer of silicon oxide has grown now. So now the oxygen has to diffuse through the silicon oxide and it has to reach the silicon oxide interface. Yeah. So here, this diffusion now creates a diffuse time limited step that determines the rate of your oxidation. So it's not like initially it was this because it's like the rate it interfaces oxidize, but now it's the diffusion. So the option B is correct. The oxidation is limited by the rate at which vapors diffuse through the oxygen. So this is correct. So the C option is energy required to break silicon-silicon bond is the barrier for both. So now as we discussed that here the diffusion is the important factor. So this doesn't like is not a rate determining thing. So the energy is required for breaking these bonds, but the rate determining step is what we are concerned about. So that is diffusion. So The last option, the diffusion barriers. That's why we see that it is like similar to this. Like in wet oxidation, we get a diffusion barrier of 0.79 and activation energy is zero point 0.7. Yeah, and this oxygen with dry oxidation step, we have oxygen a diffusion barrier of 1.18 electron volt, and while this dry oxidation takes an activation energy of 1.2 electron volt. So that tells like why this parabolic rate is like why these energy barriers are there. Yeah. And also there is no variability with the facets of the silicon. So the planes of the silicons. So silicon planes. So yeah. So this is a true or false. So there are three statements here, and you have to tell true, true, false, false, whatever. So all the three can be true, all the three can be false. Any one of them can be true. So yeah. Others also please respond to the questions. So uh, to like if anything that may be wrong, but it's good that you try and express it. Okay, first one. Anybody? Any guesses? First one. Dry thermal oxidation is faster than wet oxidation. C. No, no. First statement is true or false. It's not. It's not an option. Like I could tell statement wise. First one is true. A is false. Okay. So yeah, true. A is false. So dry oxidation is like around like five. You can get around. If I'm not wrong, it's 5 times less slower. Around 5 times less slower than the wet oxidation. So yeah, it's false. Uh, so the second one is ultra thin oxides, like less than 25 nanometer, grows faster than the Teal Grove model. So anybody? This one? So the statement B, anybody has any comments? True or false? Okay. So the option B, so we have this maybe B is false. Okay. So we have this Deal Groove model, but for very low concentrations, very low, like like very thin oxides, when it's like initial times, then we usually have a trend like this, like it goes like this. So the while the Deal Grove model tells it's linear, but actually it comes like this. So This, if in the slide, they derive it as in a Masood model. So it's a Masood model. So with that, we say that it overshoots. So basically, it is a curve like this. So it overshoots the what is given by the Deal growth model. So here it is a parabolic like kind of exponential like this kind of growth. While in this is a linear kind of growth. So it's a polynomial kind of a growth. So yeah, so this is true. So it overshoots. So with the Deal growth model, we can't define that. So we have another model called the Masood model. And the rate of oxidation of silicon depends both on diffusion and solubility of H2 and O2 in silicon oxide. So anybody? This thing? It's true. Yeah, it's true. So we know that like the two things that it has to diffuse to the silicon oxide. So if we have silicon oxide here and silicon here, so it has to diffuse through it, and also along with diffusion, it also has to get into this volume, into this like uh, into this medium. So solubility is also an important thing. So so yeah, it's true. Good, good. So this is also a simple numerical. So this piling Bedworth ratio is given, which is there's a molar volume of oxidized silicon oxide and like the molar volume of oxidized silicon and native silicon is 2.19. So you have to find what would be the thickness of oxide formed if 10 nanometer thick silicon has been consumed during oxidation. So the molar volume is given. So molar volume of oxidized to molar volume of silicon. So, so anybody? Anybody wants to try? Any guesses? Okay. Essentially, here the molar volume of oxidized versus silicon is given. Yeah. So we know that like if the area is constant, is constant for area taking because the area won't change. Area is constant. We know that for 1 nanometer for 1 nanometer of silicon, it will It like for 1 nanometer of silicon will be consumed for 2.19 nanometer of silicon oxide. Yeah, from this molar volume we can get this. Yeah. So only the length scales we are comparing. So it's a unitary thing. For 1 nanometer is of silicon, it's 2.19 nanometer of silicon oxide. So for the 10 nanometer of silicon, we get 21.9 nanometer of silicon oxide. This is the correct one. Understood? So this is a question on dopant segregation. So this is like that this deals with the different solubilities of dopants in silicon oxide and silicon. So this oxidation is done at at 900 to 1000 degree, 1100 degrees Celsius. So you have to tell the profiles, like dopant concentration profile, which is like the correct one. How the dopant concentration profile would look like. And the the condition is if the solubility of the dopant is more in the oxide as compared to the silicon. So it loves to solubilize in oxide while compared to silicon. So which one is the correct one? So the other factor is given in the pictures like slow diffusion. So there are two conditions. So you have to tell which one of them is correct. Like which one gives the true picture of the dopant concentration. Depending on these two factors. So anybody? Anybody thinks what would be the answer? Any guesses? Okay, okay we will go uh, with the solution. So here we get that the solubility of dopant is more in the oxide as compared to the silicon. Uh, so after this oxidation process, so there in this thing it should get more accumulated in the silicon oxide interface compared to the silicon one. So here we see in this first diagram we see that there is a depletion in this silicon, and there is a the concentration of dopants in silicon oxide side is more, and there is a depletion in the silicon side. In the B1, we see that that there is an increase in the silicon oxide, silicon side of with dopants, while the at the silicon oxide it is very less, like compared to both the things. Plus, it is said that it is a slow diffusion. So, like whatever we get in the whatever we get in the silicon oxide side, it doesn't like diffuses to the air very quickly. So it should be accumulated in the interface only. So out of this, the preferred one is this one. So figure A is the correct one. Yeah. So this is the fill in the blanks. We have to this which comprises of the silicon, like the different defects in silicon oxide. So uh, yeah, the options are also there. You have to match and tell. Okay. So anybody want to try first one? So the thing is this one. A is uh, Uh, so it is present close to silicon oxide interface because of silicon diffusing into silicon oxide from bulk silicon. So here we can see the diagram is also given that these fixed charges accumulate at the interface of this silicon oxide interface. Interface it is on the interface. So not on the silicon side, not the silicon oxide side, but it's on the interface. So here it is essentially fixed charges that, that is present. Okay. And they can be reduced by annealing at the end of oxide. So annealing so here we in the lecture we get about this teal triangle. In the teal triangle, we see that if we annihilate at inert uh, dry nitrogen or argon atmosphere, it goes. These fixed charges are is the consequent like the concentration is very less. So that is inert temperature, inert or ambient, inert ambient, not like high temperatures. Because the temperature here is not like factor when we do it in inert. The third statement is interface trap charges and fixed charges for silicon 100 are compared to other silicon orientations. So uh, it is for this silicon 100 plane, it is very less. So it's lower actually. And that's why silicon 100 plane, the popularity of using it has increased. And annealing in uh, dash removes interface defects by passivating silicon dangling by silicon hydrogen bonds. It is forming gas like hydrogen and nitrogen mixture. So we use it such that silicons which are like non-bounded can bind to the hydrogen. So here it's forming gas. Yeah. So essentially I think we have crossed some time today. So we should stop by this. Okay. Thank you all. And if you have any doubts, you can ask. Otherwise, you are free to leave. There were some issues with the net today, so sorry for the same.